Done. So out of these topics, do you have any doubt in upwash? Huh? Okay. Okay, you ask your doubt. Mm-hmm. Mm-hmm. Right. Hmm. Right. Right. Okay. Okay. So actually, good doubt. So you are asking that because of downwash, aeroplane is losing lift. So how aeroplane is maintaining this lift? So see, when we know that, suppose this is the aeroplane and the weight of the aeroplane is W, suppose imagine 1000 Newton, and suppose you are thinking that airplane is generating some lift and this lift is actually being reduced because of downwash, then how aeroplane is maintaining the lift? So actually, after calculation this of this downwash, everything, you should generate somewhat more lift so that you can compensate this loss, and final answer should be remaining 1000. Okay, yeah, it should be the final answer after balancing everything. So actually, what is downwash? Downwash is nothing. It is like a phenomena when your angle of attack will decrease. So if angle of attack will decrease, your coefficient of lift will decrease, and because of that, lift will decrease. So this phenomena we call as downwash. And in upwash, exactly opposite. Your angle of attack will increase, because of that coefficient of lift CL will increase, and because of that lift will increase. So this is called upwash. Now any wing, either left wing or right wing, starboard or the port side wing, they can experience downwash or upwash by several ways. So several ways means, for example, if you have aeroplane and if this wing is going down, then this wing will experience upwash, and if this wing is going up, then this wing will experience downwash. So, and other thing is, because of trailing edge vortices and wingtip vortices also, they experience downwash, but only downwash, not upwash. So now what is vortices? Vortices are like small vertices. We have small vertices. And why are they? That phenomena I have explained in the previous class, because of the pressure distribution, the air curls, and because of that. So now in today's class, we have to understand what is stagnation. Actually, stagnation is very important concept. So our today's main focus will be to understand what is stagnation. See, actually, stagnation, if you want to understand stagnation, you should understand there is something called isentropic process. Actually, in thermodynamics, we have 4-5 popular processes like isobaric, isochoric, isothermal, adiabatic, and polytropic. In all these processes, isobaric process means a process in which your pressure is constant, and isochoric means a process in which your volume is constant. Isothermal means temperature is constant. Adiabatic means you are not supplying heat, so heat supply is zero. Make sure I am not saying constant, I am clearly saying heat supply Q is zero. Means you are not supplying heat, it means you are not sending the heat into the system, you are not taking the heat out from the system. That in that kind of process you say adiabatic process. And the last one is polytropic process. Any process when it will not match with these four processes, we say that is polytropic process. Anyway, roughly you can say in polytropic process there are some thermodynamic issues, so I'm not going into this detail. So my point is, out of this process we have to focus on this adiabatic process. Actually, in adiabatic process your heat transfer is zero. If your heat transfer is zero, then there is a term called entropy. Actually, this entropy means we don't have to go to the deep to understand entropy for your syllabus, but one small idea is like, whenever anything is happening, for example, suppose you are designing any aircraft, or you are designing any engine, or you are designing any fan, or you are designing any fridge, cooler, AC, TV, anything. So on paper when you design things, or in the software when you design things, then in that design thing you don't consider friction, and you don't consider losses, and you don't consider some real life phenomena. In whenever we calculate any question on paper using theoretical numerical, that time we go without the real touch. We only go with the assumptions. So that time our data will come something else, our answer will come something else. But if the same thing you will do in case of real life, so in real life your answer will not match. So actually your real life data will not match with your ideal data. Why? Because there is something called heat transfer, there is something called friction, and there are some more issues. Because of that we face change in entropy, means we face irreversibility. Now see, whatever I am trying to explain here, if I will summarize this, then I will say only in this way: ideal process or ideal situation is not equal to real situation. Why real situations are not equal to ideal situation? Because there is a term called irreversibility. So irreversibility is there in real process. Actually, we should not go what is irreversibility, we should go who is producing irreversibility. So heat transfer, friction, and hysteresis, and viscosity, and like there are some lot of other ways in real life we experience irreversibility. And whenever irreversibility is there, your process is no more ideal process, it is going to be real process. So when you understand that okay, there is irreversibility, it means what? There is a property called entropy. You are going to measure the entropy. It means what? Entropy is the measurement for the irreversibility. Like in your ideal process irreversibility is not there, but in your real process irreversibility is there. So we measure entropy. That entropy will only tell you okay, reversibility is there or not. So entropy is a property, irreversibility is a phenomena. Okay, suppose you want to measure any distance, that distance you will measure in terms of length, width, height, like this. In same way, irreversibility, when you will measure like entropy. So see, in ideal cases, your change in entropy is zero. You don't have any change in entropy. Like you can see here, if your pressure is constant, then change in pressure is zero. If your volume is constant, then change in volume is zero. If your temperature is constant, then definitely temperature will not change, temperature is zero. So there is another process that is known as isentropic process. I have not listed this isentropic process here because isentropic process is actually nothing but your change in entropy is zero. It means your entropy is constant. Whenever this kind of process we face in our daily life, that time we say, okay, this is ideal process. Because in real process, entropy will definitely change. So entropy change will not be zero for real process. I will summarize again. See, there is something called ideal process. Ideal process is nothing but the paper process like this. But we have real life. So what is difference between ideal process and real process? There is a term called irreversibility. Okay, what causes irreversibility mainly? So mainly your irreversibility is because of heat transfer and because of friction. These two are the main causes to bring irreversibility in any system. So that's why your real life data will not match with ideal data. So we want to know that my real system is irreversible, but how much irreversible? How much irreversibility is there? So to measure that how much irreversibility, we introduce a property that is called entropy. So this entropy change in entropy, del S, will give you that, okay, this much entropy is being changed. But if this change is coming 0, then you will say, okay, process is ideal process, and immediately you will add a name here that is called isentropic process. So isentropic process means your change in entropy is 0. Why I am teaching this isentropic process here? Because to understand the concept of stagnation, we use a word isentropic. So that's why we should know what is the meaning of isentropic. Okay. Now this isentropic process, we have to go one more step in deep. Actually, see, there are two types of poor people. One poor people who is not earning money, so that's why not able to save money. And one person is who is earning money, but whatever you are earning, everything you are spending. So again, you don't have any saving. So your saving is 0. It can be because of these two situations. Maybe you are not earning money, or you are earning money and the same money you are spending. I am trying to relate this thing. If your change in entropy is 0, then it can be because of two things. Maybe really your change in entropy is 0, or maybe it is because of whatever heat transfer is there, that heat transfer is balanced by friction. It means whenever friction comes into picture, your entropy increases. And whenever you heat take out of the system, your entropy decreases. It means decrement in entropy because of heat rejection and increment in entropy because of friction. If this amount is equal, then total change in entropy will be 0. So this process you can say as isentropic process. But there are certain examples where your directly change in entropy is 0. What I am trying to summarize here, your heat transfer is 0. It means this is called as adiabatic process. If your heat transfer is 0, then you will say adiabatic process. And if your friction is not involved, then you will say reversible process. It means there is nothing to make irreversibility. So they both together we call as isentropic process. So means your adiabatic plus reversible. Reversible process is nothing but ideal process. And adiabatic process means a process in which your heat supply is 0. Adiabatic plus reversible, if both are happening together, then your entropy will not change. Then this you will say as isentropic process. And adiabatic plus reversible process is isentropic process, but isentropic process is adiabatic or reversible. It is not possible every time. It may be, it may not be. It means adiabatic plus reversible process is isentropic process, but vice versa is not true always. Sometimes it can be true. Okay, actually, because I have to explain the stagnation, that's why I'm going into this part, but this part is not directly affecting your topic. But now I think we can jump to our stagnation point. What is stagnation? So see, actually what happens? Whenever there is a flow, either in any pipe or over any surface, whenever there is a flow, then that flow will be having total 3 types of energies. All the possible energies I'm talking, total 3 types of energy is possible in any flow. You may have, there is something called enthalpy, symbol is H. You may have, there is something called kinetic energy. You may have, there is something called potential energy. So whenever there is a flow, in that flow you will be having three types of possible energies. More than this is not possible, less than that is possible. Maybe your potential energy is zero or something is possible, but more than that is not possible. So imagine if the flow is happening like this, flow is going in this direction, same thing you consider here also, flow is going in this direction. Then you bring the flow to the rest. You bring the flow to the rest. So when you are bringing the flow to the rest, then this rest word you can say as you are making the flow to be static. Okay. And when all the molecules will not move, then what will they do? When all the molecules will not move, then we will say a special word. We will say that our entire molecule are stagnant now. Are stagnant. So the location where this will happen, that location you can say as stagnation point, and this phenomena you can say stagnation. I will explain again. Whenever there is a flow happening, that flow will be having three types of energy: enthalpy, kinetic energy, and potential energy. So what will happen? There is a concept. That concept says bring the flow to the rest. Means all the molecules were flowing in this direction, but now stop them properly. So when you will stop these molecules properly, what will happen? You are going to achieve a condition. You are going to achieve a state. You are going to achieve a phenomena. You are going to achieve a situation. That situation is nothing but all the molecules are being stagnant. Stagnant means everyone is being stationary. Now, whenever you use word stagnant, that time we should use we are bringing the flow to the stationary condition in isentropic way, like isentropically. Why are we using the word isentropically? Because this isentropic word means you don't have heat transfer and you don't have irreversibility. It means your flow is happening adiabatically and plus reversibly. It means what? When you were bringing the flow to the rest, that time any amount of heat did not go outside or any amount of heat did not come inside. At the same time, when we were bringing the flow to the rest, then there was no friction involved between the layers of the molecules or between the wall surface to the molecules. So there was no heat transfer, there was no irreversibility. It means adiabatic and reversible. It means combinedly you will say isentropically. Means whenever there is a flow happening, that will be having some certain energy. All the energy is being converted into pressure energy. All the energy is being converted into pressure energy. Enthalpy, kinetic energy, potential energy. So you are converting all types of energy into pressure energy, but using which process? Isentropic process. Isentropic process means reality is adiabatic plus reversible. Adiabatic, what is adiabatic? When you are bringing the flow to the rest, that time any heat is not going out, any heat is not going in the flow. Till now, do you have any doubt in this? Okay. 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 Then you see. Okay. Okay. It means story clear. Okay. Very good. Story is clear. So just few seconds. You see what is the T diagram. Actually, if you want to understand the stagnation concept, then you should know isentropic process. Actually, what isentropic we are looking for, there are in that isentropic process, this isentropic is nothing but adiabatic plus reversible. Adiabatic means your heat transfer must be 0. When I'm using word transfer, it means it is valid for input also and for output also. And and reversible means ideal process. It means in real life we never achieve this. Okay, so according to this theory, we have to bring a moving liquid, a moving flow to the rest, and successfully if you are achieving this state or this phenomena, then you will say that your flow became stagnant. So at which point it is happening, that point is known as stagnation point, and this phenomena will say as stagnation. Okay, now where can we see this? So for that I will change the page. See, if we have any airfoil or if we have any sphere, suppose this airfoil is moving in this direction, then whatever flow will come, if I draw any streamline, I'll draw like this, I'll draw, but there will be a point where your streamline will hit and it will vanish. This is streamline, you cannot go inside, and maybe your next streamline will pass like this. And just in case of a sphere, imagine this sphere is circulating in this direction, and because of that whatever flow is coming, that flow is going like this and hitting the sphere here, and the next layer of flow is going like this and it is going like this, and from here one flow is leaving the sphere, and maybe your next flow is going like this. Okay, so here the flow is going. So I'm trying to say a point where the flow is coming and being stagnant. So that point is this point in this diagram, and this point and this point in this diagram. So at these points, what is happening? Whatever flow is coming, that flow is going and being stopped. Here this flow is going and being stopped. Here from stationary the flow is leaving. So these points are known as stagnation point. So what is common here? In the flow you will be having total pressure, and this total pressure will be exactly equal to the pressure at stagnation point. So this total pressure and stagnation pressure is going to be same when we talk about stagnation. So sometimes roughly we say that total pressure in the flow is everywhere same. So whatever pressure you achieve at the stagnation pressure, that is nothing but the total pressure of the flow. It means at this section, 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 whatever total pressure is there, that is going to be same. Means why are we dealing with stagnation? Because if you understand stagnation, then only you can understand there is something called total pressure, and this total pressure is only we call as stagnation pressure. And if you go into detail, this stagnation pressure is actually nothing but dynamic pressure plus static pressure. So if your stagnation pressure is constant, then automatically one thing is clear. If dynamic pressure will increase, static pressure must decrease. Or opposite, if dynamic pressure is decreasing, static pressure must increase. So because of this this phenomena, actually this style what I am explaining here, this is mathematically explained by Bernoulli equation. Bernoulli equation. You should know only one thing here. Your dynamic pressure is nothing but half rho v square, where rho is the density and v is the velocity of the fluid. So if the fluid is being more faster, then dynamic pressure will increase, and in the direction of the flow you will experience this dynamic pressure. So if you stand here, then this flow will take you away. For example, if you sit in front of fan, then your hair will blow like this. So this is because of dynamic pressure. Okay, so this entire concept of stagnation is only this much. Now some important points are there. So whatever pressure we find on stagnation point, that pressure we denote by P naught, or some textbooks they write P total. So this thing you will say as stagnation pressure, or you can say total pressure. In same way, whatever temperature you calculate at stagnation situation or at a stagnation point, that is T naught or TT. This is going to be your stagnation temperature or total temperature. Okay. In same way, we have density. In same way, we have some other properties. And very important part, at stagnation point, your velocity must be zero. Because why? We are bringing our flow to the rest. So there is no velocity. And if there is no velocity, then your Mach number is also zero. Now, one small revision. What is Mach number? Your Mach number is nothing but a number which relates the speed of any object with respect to the local sound speed. What does it mean? Suppose here you have any suppose here you have any atmosphere, and here you have the ground. Suppose this country is America, and suppose there is another country. Suppose this is India, and suppose here your temperature is 200 degree Kelvin, and suppose here temperature is 400 degree Kelvin. See, suppose here your aircraft is flying with a speed of 200 meter per second, and same aircraft is flying here also with same speed 200 meter per second. So actually in this atmosphere, if your sound will travel, then speed of sound will be according to this temperature. But in this atmosphere, if sound will travel, then speed of sound will be because of this temperature. And if your temperature is more, then your speed of sound A will be more, because it is directly related. So just for reference purpose, I am giving a formula, and A is equal to under gamma RT. If your temperature is more, your speed of sound will be more. A is the symbol for speed of sound. And your Mach number is local velocity of the object divided by sound speed in the atmosphere, in that local atmosphere. So for this situation, if you will calculate the Mach number, that Mach number is nothing but speed of the aircraft divided by speed of sound, which hit this sound. So you can see this temperature is more, so this sound will be more. So if A value is more, then Mach number will be less. In same way, you see here in the second atmosphere, here temperature is less as compared to this. So here your sound velocity will be less as compared to this. So here your Mach number will be more. It means what you see, your speed is 200 meter per second, but your Mach number is not same, because Mach number depends on two things: your velocity and the temperature of the atmosphere in which you are flying. Mach number is not simply the comparison with the sound speed. Mach number is actually the comparison with the local sound speed. Actually, if you will target Google, so on the Google, if you will type speed of sound, so it will roughly come 343 meter per second, roughly, in the air, speed of sound. But see, reality is this speed of sound is not equal everywhere in the atmosphere. Why? Because in the atmosphere, your temperature is not same everywhere. So your A value will not come according to gamma RT formula. A value will not come same everywhere. So that's why this is just an average value. Simply like we say, okay, there is something 343 meter per second speed of sound. But this speed of sound you cannot take for granted for Mach calculation, Mach number calculation. So in this entire thing, I wanted to say only one thing. At stagnation, your velocity is zero, so your Mach number is zero. But Mach number depends on two things: velocity also, and divided by under root gamma RT, it means temperature also. So here Mach number is being zero. Why? Because velocity is being zero. Why I am teaching this part? Because 1 by infinite also gives you zero. So some people may give you wrong logic that your temperature became infinite, that's why 1 by infinite is giving zero. But no, this is wrong logic. Mach number is being zero at stagnation because your velocity is being zero. Okay. So this was the complete idea about stagnation. Now we go for the terms: camber, chord, mean aerodynamic chord, profile, and parasite drag. One by one we will take. So actually, what is camber? Actually, these terms are coming from airfoil. So whenever, what is airfoil? Airfoil is a streamlined body. When we say a streamlined body, what does it mean? Meaning is, your streamline, one single streamline will cover the body properly. It will not break in between. This is the meaning of a streamlined body. If your body is not streamlined, then what will be the name? The name will be bluff body. Okay, like this kind of object is flying in the air, this you can say bluff body. So when when aeroplane or aircraft is flying in the air, everything whatever we introduce it on the upper surface, everything should be streamlined. Why are we looking for a streamlined body? Because streamlined body are having one main feature, less drag. They produce less drag. Why are we looking for less drag? Because whenever you want to move further, then in back direction, as less as possible forces we should keep. So nature will provide you friction in backward direction. Whenever we travel, we get friction. Whenever something flies in the sky, because of friction in the air, that is called viscosity, we feel drag in the opposite direction. There are some other ways to discuss drag. When the point will come, I will explain properly, because drag is there in our syllabus. So currently you just understand, whenever whenever we talk about airfoil, what is that? It is a streamlined body. What is the meaning of that? Your streamline will completely cover the object like this. Okay, now see, we have to go to the detailed part of the airfoil. Means, if we have any airfoil, then you have leading edge in the airfoil and you have trailing edge in the airfoil. What is leading edge? Leading edge is the first line of the airfoil, exactly the first line of the airfoil. Actually, in 2D you may not understand the leading edge. I will draw the 3D. 3D means this is one airfoil, then it is a wing, actually completely wing. In 3D it is a wing actually. Then from the wing, your fuselage is attached. It means your fuselage is attached like this, so you have the wing here. So in the wing, if you cut any section like this, then you get airfoil shape. It means this shape is airfoil shape. So in that airfoil shape, you see this part that we call as leading edge. So when you see from this side, lateral side, you can see only this part. So that's what I'm saying, leading edge. So leading edge is not any point, it is actually complete line. So backside we have trailing edge. Okay. So leading edge and trailing edge, when you will connect them like this, then you will be getting a chord line. So see, according to the shape of the airfoils, like some airfoils are like this, 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 some airfoils are like this. So when you connect the leading edge and trailing edge, then you get chord line. Connect leading edge, trailing edge, you get chord line. Connect leading edge and trailing edge, you get chord line. Connect leading edge and trailing edge, you get chord line. Leading edge and trailing edge, you get chord line. Now you can see, sometimes your chord line is cutting the airfoil surface because it is imaginary line, and sometimes it is not cutting the airfoil surface. Now, what do you mean by camber? Camber means, what do we know? What do we do? Upper surface and bottom surface. I'm using black color. Upper surface and bottom surface, they will be having, there will be a line. That line will divide them equally. For example, if I am drawing the green line here, then just imagine this green line is dividing upper surface and bottom surface at equal distance. You can see, I am trying to say this distance and this distance is equal. This and this equal. This and this distance equal. This and this distance equal. Equal. So how do we achieve this? So you do one thing. Like at every point you keep on drawing the circle. At every point you keep on drawing the circle. Circle. So actually in case of circle, we have center, and center divides diameter half, exactly half. So then you connect center, and you get camber line. Okay. So after connecting all the centers, you get camber line. You see, in case of my first diagram, if I draw circle here, 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 so this circle is separating equal distance of the upper and bottom surface, upper surface, bottom surface, equal distance. So that will lie, centers will lie here. So if you'll connect them, then your chord line itself became your camber line. So I'm using two words here. One word I'm using CHORD, chord line, and one word I'm using camber line, CHAMBER, camber line. So see, camber line is different and camber is different. So whatever I have done now, that is camber line. Okay, and what is camber? Okay, I'll come to that. What is camber? Now notice the point. Sometimes your camber line may lie on chord line itself. Sometimes your camber line may be above of the chord line. Sometimes your camber line may be below of the chord line. Sometimes your camber line may go like this also. Okay, so before this and after this. Okay, and camber line like this. So this is a camber line. Now what is camber here? Now camber line is a line, but camber itself, only the word camber, it is a distance. If I will say camber, only camber. So camber is a distance. What distance? The maximum distance between chord line and camber line is known as camber. It means in this case this, in this case this, in this case 0, in this case maybe from here to here, or maybe from here to here. Okay, so you are getting what is the camber. Camber is the distance between chord line and camber line, but not any distance. Means I'm trying to say here also you have distance, 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 but I'm looking for the maximum distance. So that we say as maximum camber. Maximum camber we simply say as camber. We have so many cambers, but our special target camber means maximum camber. Okay, so now you see, if we are clear with the camber line and maximum camber, then we should know what is the use of this camber and maximum camber. Actually, these people are helpful to decide coefficient of lift at different angle of attack. But those things are different. They are a little bit technical. But you should know why are we bothering about camber, because that will decide the amount of coefficient of lift according to the angle of attack. Okay. So this is the idea about camber. Now what is chord? Just now we cleared. Now what is your mean aerodynamic chord? This is actually very practical question. So I will explain this. See, we are going to understand mean aerodynamic chord. There is a word called mean here, MEAN. Whenever mean word is coming, you must keep in mind it is similar to average, some kind of average. So mean aerodynamic chord means, suppose there is any family. In this family 3 people are earning. I'm talking about the family. In this family we have man 1, man 2, man 3. So if man 1 is earning 1000 rupees, man 2 is earning 1200 rupees, man 3 is earning 1400 rupees. So can I ask what is the average income of the family? So if I'm asking average income, so I will say average income of, sorry, income means I, average income of family. So if I have to find out AIF, average income of family, what will I do? I will add 1000 plus 1200 plus 1400 and I will divide by 3. So that is going to be your 1200, the middle answer. So 1200 is the average income of the family. It does not mean everyone is earning 1200, but it is similar to the same thing that everyone is earning 1200. Similarly, we have mean aerodynamic chord. It means what? Reality is, in our aircraft, suppose this is the aircraft, whatever wing you design, actually at the root you use different airfoil, and at the tip you use different airfoil. So in every airfoil you have chord line. Suppose I am drawing any airfoil here, suppose I am drawing any airfoil here, and I am drawing any airfoil here. So you can see chord line is not same in every airfoil. So there will be a method. Because of that method, I will find out mean aerodynamic chord. And you try to understand, like in my previous example, man 1 was earning 1000 and man 2 was earning 12,000 and man 3 was earning 1400. So when you found the average salary of the family, then we got 1200, right? So this 1200 is actually matching with someone. Maybe it may not match with someone, but in this example it is matching with someone, right? So this man became average salary, which is represented by the family salary. In same way, when we are finding out mean aerodynamic chord, there is a big formula. So that answer comes something. So actually that answer also matches with a particular airfoil. So that airfoil we call as mean aerodynamic chord. I mean chord of that airfoil we say as mean aerodynamic chord. Okay. So for every airfoil we have chord length, but those chord lengths are not same. So we have a procedure through which we calculate our mean aerodynamic chord with a formula. So whenever we find the answer, then that answer will actually match with the real chord of any airfoil. So that chord we call as mean aerodynamic chord of this wing. Okay. Then we go for profile or parasite drag. What is this? See, whenever we design our aircraft, so suppose this is the aircraft. So if you see the aircraft from the front, so it will look like you got your fuselage, and then you may got your tail, and you may draw your wing like this. Okay. When aircraft is going in this direction, then air is directly hitting on the front surfaces of the aircraft everywhere. It means everywhere air is hitting. So it is like this entire machine is going in this direction, but some air is coming and that air is hitting in all these areas. So because of this entire aeroplane will experience force in this direction. Why? Because your force is nothing but pressure divided by area. So now you see, if your area is more, sorry, just a minute, your pressure is equal to force by area. So multiply area here. So force is equal to pressure into area. So from here you see, if your area is more, then your force will be more. Area is more, force is more. It means when air will hit here, everywhere, so air will apply pressure. So that pressure will take the aircraft in back direction. So how much force aircraft will experience in this direction? That force we call as drag. But we have several types of drag. Parasite drag, profile drag, induced drag, wave drag, ram drag, shockwave drag, I mean supersonic drags. So they all are there. But the basic drag, what we achieve first time, that comes with the design. With the design means once the aircraft is ready in the companies, then it means what? Design is fixed. So this aircraft is going to experience minimum that much drag. Minimum. So other drags will come after this. If this aircraft will fly faster at supersonic speeds, then shock waves will come and something will happen. Extra drag will add. But minimum this much drag will come because of the profile of the aircraft. What is called profile? This outer line what I have done here, this is called profile of the aircraft. Like how your aircraft looks like. What I mean, is, yeah, I'm trying to say that, see, whenever there is a lock, in the lock you have some holes. That holes are having some particular shape. So this is the profile of the key. Any other profile key you cannot insert in this. It means this area is fixed area. In same way, once the aircraft your design is done, then this much area is fixed now. It means what? You can simply draw an outer line like this. So this is the airfoil of the aircraft. So this much area will experience a drag. So that drag we call as profile drag and parasite drag. That's all done about that drag part. Now you see. Yes. We put or there. I mean, your parasite and profile, it's like they are or. I mean, they are the same thing, exactly same thing. But when we go detail, then we see that okay, they are not exactly same, but still there is only some small issues when you go to high class aerodynamics. There we have something there we explain, okay, they are actually not same. So now that's all about this drag. There is one another topic. Do you remember that topic name? Actually, because I have erased this part. Just after that, do you remember what was the topic? Can you see your PDF? What was the topic? I forgot the topic. Yes. Yeah, you just check and please, because this is aerodynamics syllabus we are talking, right? Okay, I got here. Yeah, I got here. So just after profile and parasite drag, we have induced drag. So now you see, we will start our discussion about induced drag. Now see. What is induced drag? Let's understand. To understand induced drag, we should understand airflow over the wing. And induced drag, we cannot explain for the airfoil. Induced drag is only related to a complete wing. What is difference between airfoil and wing? Airfoil is just the cross section of the wing, like how the wing looks like. Only that section, like it is a 2D body like this, right? But when we talk about the wing, it is actually the 3D object. So whenever we have a wing, and suppose this side you have fuselage attached, so you forget the fuselage. Suppose the entire flight is going in this direction, then entire wing will go in this direction. Then actually what will happen? There will be a flow passing over the airfoil. So currently I have done flow like this. This is the wrong diagram. Why this is a wrong diagram? Because in this diagram, I have not introduced this is called something called induced drag. So let's understand what is induced drag. So first thing you keep in mind, induced drag is nothing but drag which is coming into picture because of downwash. Now, in last class, we have covered what is downwash. So just now in today's, I have told you that whenever there is a downwash, then alpha will down, I mean alpha will decrease. CL will down, I mean CL will decrease. Lift will decrease. Now see here, lift is decreasing. It means what? Earlier there was some lift, but because of downwash, your amount of lift decreased. So how much lift is decreasing? According to that amount of lift, equivalent to that, we are going to achieve drag in opposite direction. So that drag which is coming because of reduction in lift, that lift we call as lift induced drag, or in short, induced drag. Now we have to understand how this phenomena is happening, how downwash is decreasing the lift, and because of that, how we are getting this extra drag. So, for that, you understand there is a wing, and whenever there is a flow going on the wing, then backside we have trailing edge vortices. On the trailing edge we have vortices. What is the role of these vortices? What these vortices are doing, actually, when the air is coming like this, these vortices are coming and pressing the air downward. So because of that, this air is turning like this. Okay, and this is the arrow which is representing that your trailing edge vortices, or you can see this downwash, is pushing your main this free stream, and because of this you are getting this local free stream, I mean changed free stream. Now because of downwash, your free stream arrow is tilting like this, and if your free stream arrow will tilt downward, then you should understand how lift is acting. So actually, when you see here, when your air is coming and going straight, then your lift will act like this, perpendicular to the free stream. But when the downwash effect will come into picture, just a minute, I'll explain this. When the downwash effect will come into picture, then your local line will turn. I mean, this was your airflow. That airflow will turn in this direction. How it is turning? Because of the downwash acting in downward direction. So by certain angle, it will turn like this. Okay. So actually it is a rule, and rule is your lift is always perpendicular to the free stream. So earlier, this black color lift line, now this line was actually perpendicular to the red line, but now the red line is turning and becoming the green line. So because of that, your lift vector will also tilt like this. So we'll be getting a new lift vector. Now in this new lift vector, you will be having two components. One component will act perpendicular to the free stream, and one component will act in the direction of free stream. Okay. So now you see this thing, the blue line, what we are getting in backward direction, that is only taking the aircraft in backward direction, or trying to take the aircraft in backward direction, or pushing the aircraft in backward direction. So this arrow is coming because of this tilted lift vector as a component. So that's why tilted lift vector is nothing but the lift. So that's why this arrow is being induced because of lift, and because its nature is in backward direction, so we call this arrow as induced drag. Why do we call this as induced drag? Because it is inducing. Why? Because of lift. What is the main cause? Downwash. Who is producing downwash? Trailing edge vortices, wingtip vortices. They are responsible for the downwash. So if in real life, whenever we have a wing, we have this kind of situation, and if your wing size is changing, then amount of downwash will change. Like if your aspect ratio will change, if the width and chord, if anything will change, then all these phenomena will change. Because of that, your all this situation will happen. See, if I'll summarize, then you should go like this. First, because of the trailing edge vortices, downwash will come. Because of downwash, your local free stream velocity will turn. If local free stream velocity will turn, then your lift vector will turn. If lift vector will turn, then it will give you two components. Out of that those two components, one component will be in the opposite direction of the forward motion. So because it is in opposite direction, so it will behave like of drag. This is happening because of lift. So this drag we call as lift induced drag, or simply we say induced drag. So in case of subsonic motion, we have especially only two types of drag. One drag, just now we discussed parasite drag, or you can call this profile drag, plus one extra drag, that is called induced drag. So these two drags are generally in all the flights. There are some more drags, they are in special cases. Every time those drags will not act. So for example, wave drag. So those drags will not come every time. When your flight is being supersonic or some maneuvering, that time some extra drags will also being added in the total drag equation. So mainly, especially we have parasite and induced both. Now parasite drag and induced drag, they decreases with respect to speed. So for that also we have some variation, like at low speed which drag is more, and at more speed which drag is more. So something like that. Okay, so that's all for today, and I hope you have understood what is induced drag. And in next class I have to explain the airflow variation. I think already I have given you that pressure concept, right? Why trailing edge vortices are happening according to the pressure variation on the lift. Yeah, so then no need. Just 1 minute. Actually what I'm trying to say that mainly over the wing what happens, here your pressure is low, bottom the wing pressure is more, and here pressure is like common for both. So it's like here pressure is 12, here pressure is 10, here pressure is 8, this kind of phenomena. So this 8 is a common for both, this 10 is common for both. So because of that, whatever air is near to the tip on the upper surface, that will turn towards the root. But whatever is the air which is below the wing, that will turn towards the tip. So this makes this kind of curl motion that we say as vortex. That's all. This is the vortex, and this vortex will affect the incoming air. Okay, then this incoming air will tilt. Because of that, lift will tilt. Because of that, we get extra component in opposite direction that we call as induced drag. That's all.